This example allows us to learn about a transformation called reflection. Reflection should be intuitive. If you can imagine a body of still water, maybe a pond with trees surrounding or mountains, and you can see the reflection of the mountains and the trees perfectly mirror imaged upside down on the pond. And that's a reflection, and reflections work similarly in that way, graphically. And first example here, we have a transformation of the original parent function, the absolute value of x. The transformation is transformed because there is a negative coefficient in front of the function, or in front of what would be the parent function. So that parent function would have normally had 0, 0, 1, 1, negative 1 and 1, because the absolute value of negative 1 is positive 1. Absolute value of 2 is 2 units away from 0. Negative 2 is also 2 units away from 0. 3 units away from 0. Negative 3, also 3 units away from 0. So that's what absolute value is. It just tells us how far from 0. So it's always positive because it represents a distance from 0. And that's what our original parent function would look like. Once you put a negative in front of it, though, it'll be reflected across the x-axis, or reflected upside down, which is what we call a vertical reflection, or sometimes, like I said, we would just say it reflects across the x-axis. So to see this, let's do an xy chart. And I think I'll do ordered pairs, x and f of x on one side, and the transformed version, x and g of x, on the other side. Okay, so f of x, we saw plugging in 0 gave you an absolute value of 0 is 0. Plugging in negative 1 gave you, or actually let's go positive 1, gave you absolute value is 1. Negative 1, absolute value is 1. And it works similarly as you go. For g of x, though, now there's a negative out front, so the origin is still going to have the point on it. But then, when I plug in a positive 1, after I apply the absolute value, so the absolute value of 1 is 1, there's a negative out front that gets multiplied on that positive 1. So this gives us a result of negative 1. So what just happened there is where I would have been on the original parent function in the first quadrant, now I find myself in the fourth quadrant, or across the x-axis on upside down reflection. All right, let's do another one. Let's see. For plugging in a negative 1, I would plug in negative 1 here and apply the absolute value, which would make it positive, but then that negative is applied, so I end up with negative 1. So this point on the original parent function has been reflected across the y-axis. And we'll see that this pattern continues until we have a perfectly reflected upside down version of the original. So that's a vertical flip, or a reflection across the x-axis. Now for this example, the negative is actually on the inside of the absolute value. So let's see what happens with this one. So the original, we know, like that, and we had ordered pairs, x and h, and we'll compare those with ordered pairs x. Oh, rather I want to do x and h and compare that to the original x and f, where f is still the original parent function. So again, we have 0, 0, 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2, negative 3, 3. For the blue version, okay, plugging in a 0 here, I'm going to have the absolute value of 0, negative 0, which is absolute value of 0, which is 0. So again, we have 0, 0. Okay, let's see. Let's plug in positive 1, so we'll go negative. There's already a negative there. Now I'm going to put in a positive 1. So that is, the absolute value of negative 1 is 1. So I actually ended up still getting a positive 1. So that would be here. Okay, let's do negative 1 and 1. I'm going to plug in a negative 1 here this time. So that would end up being a positive 1 inside the absolute value, but again, positive. So with an input of negative 1, I still got an output of positive 1, so I'm here. And this is going to continue in this way until we have another absolute value function that is directly on top of the original parent function. And we call this a horizontal flip because we were inputting the values of x from the opposite side. For instance, where we would normally put in, say, a positive 1 and find the absolute value of positive 1, we were finding the absolute value of negative 1 and ending up with the same y value. So it's a little harder, I think, to wrap your mind around a horizontal flip that already was symmetric across the y-axis, because what I mean by symmetric across the y-axis, just to make sure we're all on the same page here, is I can fold this thing along the line. If you can just take the paper and fold it along that line, these two sides will match perfectly. They'll line right up. So being that the absolute value function is already symmetric to the y-axis, when we have a horizontal reflection, it ends up being exactly the same because it just gets twisted around, kind of flipped upside down, and not upside down in the sense of, what I mean is, if you could take the paper and flip it over, then you would have the same picture, but it would have been flipped, kind of like spinning it on the y-axis. So this is a horizontal reflection, and that's what happens when you have a symmetric, original parent function that was already symmetric. So I guess just to leave it as the original. Okay, so that's that one. What's more interesting, I think, is a function. So I'm going to make up a new example. I'm going to make up a new example and call it C for this, 2C. And I guess I'll call this K of X is X cubed. And, or let's say it's negative X cubed. How about that? Where the negative is on the inside. Then the original parent function would have been, so to kind of split it up from this. So the original parent function would have just been plain positive X cubed. Alright, so that would have original points. Let's make the transformation in blue just to help keep these things separate. So K of X is so the original x and f, where f is x cubed, you would have had 0, 0 cubed is 0, 1, 1 to the third power is 1, 2, 2 to the third power is 8, and then we have negative 1. Negative 1 times negative 1 is positive 1. I'll show you. Negative 1 cubed is negative 1 times negative 1 times negative 1, which is positive 1 times negative 1, so you get a result of negative 1. And then negative 2 becomes negative 8 for the same reason. 3 negatives, any odd number of negatives being multiplied results in a negative. And so just to do a few, I guess I'll plot that. So we have 0, 0, 1, 1, negative 1, negative 1, 2 and 8, negative 2 and negative 8, and then we get a shape that is like a squiggly kind of snaky looking thing through the origin. It's odd. It has end behavior that goes opposite. One end goes up, one end goes down. And then the blue version, again, when you plug in a 0, 0, negative 0 is just 0, 0 cubed is 0. So the origin still has the middle of this thing, which is a turning point. And then we have positive 1, but if I put in a positive 1 here, there's a negative out front of it now. So this will be negative 1 quantity cubed, which we know is negative 1. So now 1 will not be paired up with positive 1 anymore, but with negative 1. So we're down here. And then 2 will be paired up with negative 8. And negative 1, if I put in a negative 1, right, so there's my negative with the space for the x input, and if I input a negative 1, then this becomes positive 1 cubed, which is positive 1. So now, instead of negative 1 being paired up with negative 1, it is now paired up with positive 1. And the same thing's going to happen with negative 2. It's going to be paired up with positive 8 rather than negative 8. So negative 1 and positive 1, negative 2 and positive 8. So now we see the same shape and everything, but it is flipped. And we would say this is it qualifies as a horizontal reflection because, let me finish making this thing look decent. We would consider this a horizontal reflection because you can see that now where we had a point here, we have a point symmetric to the y-axis over there. A point here, we have one symmetric to the y-axis over there. And here, over, and so on.